And let me pull up my slide deck and we can get started. So I'm pleasantly surprised. So did you already do an introduction, or do you want me to do that myself?
You can do a brief one, but Dr. Sinha did a brief, short one for you, but you're more than welcome to give us a quick update on yourself.
Okay. Well, great. Well, good afternoon. Darren Austin with Mueller Water Products. I've been with the company for, let's see, 7 years. I run what we call a our water management solutions team. And I'm a licensed professional engineer in the state of Tennessee, and been focused on really marketing and providing solutions for civil engineering products for my career. So without further ado, the presentation today is on assessing pipeline conditions using acoustics. So appreciate the opportunity to present. You know, obviously, we're all professionals in the water industry. Main breaks cause disruption. They disrupt people, traffic, business. They obviously interrupt the news, and they also, and unfortunately, interrupt or disrupt public confidence in our water system. So, and for those of us that are on call in the middle of the night, they also interrupt and disrupt our sleep. So the challenge is that how can we find the weakest link in our water distribution network before they find us? So on this slide is an excerpt from the Fulkerman study, Utah State from 2018. And, you know, we first need to understand what's in our system. And so, you know, from this study, it's no surprise that cast iron and asbestos cement pipes fail most often. According to the study, that particular category, or those particular categories of pipe have increased by more than 40% from 2012 to 2018. So, you know, as a result, it's no surprise that these two categories of pipe are the target for most replacement projects. And as a matter of fact, 50-year-old plus cast iron pipe represents 20% of all the installed pipe in the US and Canada, or in North America. So the replacement costs range, of course, from $1 to $2 million per mile. However, there's some technology using acoustics, such as what we call our Epulse technology, that works very well at finding leaks and measuring the remaining wall thickness on these particular pipe types. And at a cost of less than $30,000 a mile, it represents only about 1 to 2% of the total replacement cost. So it's a very economical way to go about assessing the condition of your pipe from outside the pipe. So, you know, water utilities are always seeking ways to be smarter. With the $15 billion or so that's spent annually in North America to improve water distribution pipeline systems. They want data to help decide which pipes to work on and what types of action to take. And they want to do that for the most part without inserting tools or interrupting the water supply. So the last thing a water utility wants to do, right, is replace good pipe. There's a lot of time spent on planning capital projects to replace pipe. A lot of time that's spent designing pipe replacement programs. So we want to use some of that money to determine the condition of the pipe before we start replacing these projects, or these pipelines. So I'm going to introduce you to a term called Epulse. It's an acoustic-based technology that helps utilities assess pipeline conditions without inserting any tools into the pipeline. It basically measures remaining wall thickness. And the tool that we use is a correlator. You can kind of see the receiver up there, the transmitter 1 and transmitter 2. And the way this correlator work, which we call Leak Finder ST, it's these sensors that are attached are generally smaller than a Coke can, and they attach to the outside of the water pipe, either to a hydrant or possibly through excavation directly to the water column if the sensors need to be placed closer than what the hydrants will allow. So generally these sensors are placed about 300 to 500 feet apart, and technicians measure the amount of time it takes for sound to travel between the two sensors. Then that velocity, the wave propagation velocity, is fed into our proprietary algorithms, along with other site information like pipe diameter, material, lining condition, in order to determine the remaining wall thickness. So an Epulse pipeline condition survey also includes an acoustic leak detection for each segment of pipe. So what you end up having is a leak detection survey as well as a remaining wall thickness. So here's how the process works. A sound is induced either between or adjacent to the two sensors. That's picked up by the receiver, and the speed of sound is recorded in the laptop computer. This is what it looks like in a little more closely. The kit includes the transmitter, 2 sensors, 2 hydrophones for use on certain types of pipe, and then magnetic sensors that are attached to the metallic pipes. So in many cases, this correlator, which we call Leak Finder ST, is paid for very quickly by the utility just based on the amount of leaks that are found in just a few segments of pipe. So this is kind of what it looks like in the field. What you see here, let me make sure everybody can see here. What you see here down in the lower right corner and off into the distance are 2 Ecologics technicians attaching sensors to either, in this case, a valve box and a fire hydrant, and then inducing a noise, and then it's measuring the speed in which that acoustic wave travels throughout the pipe. They flow a small amount of water, which this test flow creates noise. It's picked up by one sensor first and then the second sensor. And so that from there, the velocity measurement can take place. Because the kit is battery operated, portable, and attaches to existing fittings outside the water pipe, it's easy to adapt the technology to different types of pipe networks. In some cases, as I mentioned, we may need to excavate potholes to actually attach the sensors in between long distances of pipe. So this is a technique that's used probably on every 3rd project that we're involved with is potholing. So a lot of people will ask about pitting and corrosion, tuberculation, and graphitization. So because tuberculation and graphitization does not contribute to the structural thickness of the pipe, that's actually ignored in the calculation. Pitting and corrosion, on the other hand, will impact the speed in which the sound travels through the pipe. Therefore, it'll impact the Epulse measured pipe thickness. And again, the key here is this is survey level technology. Results from an Epulse survey are not going to be able to pinpoint the thickness along the length. What's reported is really, it's a minimum average wall thickness around a length of pipe. So it is a survey level but it's a very economical survey level assessment from outside the pipe at about $30,000 a mile. So this minimum average wall thickness over the length of pipe to be tested sometimes can be a little confusing. So if you found the thinnest remaining wall thickness around the circumference of the pipe and you average this value, that would actually be the Epulse measurement. And since most metal pipes that are pressurized degrade mostly at the bottom of the pipe, the Epulse average thickness would be conservative. It doesn't, as I mentioned, it doesn't measure any tuberculation or graphitivization that remains in the pipeline. It's only measuring the remaining structurally intact wall thickness. And the algorithms that we use in the calculation of remaining wall thickness has been validated over the past 10 years by many utility partners that we've done business with. These utility partners include Suez Water, American Water, WSSC, to name a few. So they've run hundreds of validations on the Epulse technology, comparing these independent thickness measurements with the acoustic Epulse thickness measurements. And our correlation is approximately 91%. Which is very good agreement between the two data sets. And we continue to refine these algorithms as we get more and more coupons back from utilities who want to double check that our measurements are indeed accurate. One of the additional services that we offer along with the acoustic leak detection survey and average remaining wall thickness survey from Epulse is the remaining service life. So if you think about kind of pipes like brake pads in your car, and we know how much brake pad there was when we started and how much there is now and how long it took to wear down, you can get a pretty good idea of how much longer you can keep driving your car before the brake pads need to be replaced. And it's a similar concept here with remaining service life using acoustics. Utility records give us the original installed pipe thickness. We can calculate how much pipe thickness is needed before the pipe will break. Part of this model, and again, these are another algorithm that we've built over the past 10 plus years, is requires inputs such as the soil load or the overburden, water pressure, and pipe type. So the red line kind of shows where we can add more value to the data set from the utility. In terms of different types of pipe material, we work with engineering partners for larger diameter cast iron, AC pipe, steel, PCCP, and other types of pipe traditionally used in larger diameter. So we have some engineering partners we work with for remaining service life. But all of these pipe types and diameters are well within the capability of the acoustic leak detection technology. I did mention that it's a survey level analysis. So by deploying a field crew, they can generally do about 2 miles of acoustic leak detection and average remaining wall thickness survey work in about 3 days without significant interruption or tremendous traffic control issues. And for that, of course, the clients will get in return a report several weeks later that allows them to look at for each segment surveyed, the remaining wall thickness, and if there was any leaks found, where those leaks are plus or minus 3 feet. So it is a survey level report. It would kind of sit in terms of the inverted pyramid from M77. It kind of sits just below, say, a desktop model. One of those desktop models that is becoming more popular today is kind of what's called a virtual condition assessment. So in the event that a utility wants to survey and prioritize their pipes, you know, maybe across their entire network, that can be done with AI technology or a virtual condition assessment. We call that pipe rank. So instead of doing a survey level, you know, assessment in the field, this can be done with a desktop model. And usually what we do is we gather information from 3 different categories of inputs, like utilities, which would include pipe material, age, break history, public data, which would include, you know, weather, soil, seismic activity, et cetera, and some other proprietary variables. And then an AI tool analyzes that information and develops a prioritization based upon that data. In a sense, it's basically an AI analysis. And then usually the last year of break history is withheld and then compared to the predicted break from the previous year. That's the way that we kind of can demonstrate the accuracy of pipe rank as a virtual pipeline condition assessment technology. So even though it's beyond acoustics, it's a more economical solution, even if $30,000, you know, $30,000 a mile doesn't fit into a utilities budget. So just a little bit more about myself. If you do want some additional information or have any questions beyond the conference, feel free to reach out to me with the information you see there on your screen.